So this is Rachid. This is his second SwiftSofia meet he's actually doing. So thank you, Rachid, very much. He's a security engineer and also an iOS developer. Let's say I'll let him introduce himself in the best way he figures. So yeah, basically, there's not much I can say. I'll be here for monitoring the meeting and also helping you guys share your comments. Rashid told me before that he's okay with comments while he's doing the presentation. If there's anything that's not clear enough, just shoot a message and we'll show it on the screen. And yeah, thanks Rashid a lot, because that's your free time, I'm sure. And let's hope that next meeting will be in person. So I'll let you talk now.
Okay, thank you for the welcome. And today we'll be talking about iOS reverse engineering. So in our last SwiftSofia meeting, I explained about network security, how to test your applications. And part of testing strategy is actually always, to a degree, reverse engineering, especially if you don't test your own application. And as for today, it will be a very hands-on presentation in comparison to the last time. Last time, I think it was quite a lot of slide decks. And this time, we will only have a few slides, and most of it I will be presenting from the console or from Xcode or from my phone. And so there will be a lot of switching between windows. And if you have any question during the presentation, make sure to send it with the chat, and maybe Dejan, you can interrupt me if it's something important or I'm missing something, because I don't see the chat window all the time because I'm switching between the windows.
Okay, yeah, I'll make sure I'll read the messages and let you know if there's anything.
Okay, I'll start by sharing my screen actually, and then switching directly to the slides. That's Xcode. And here we are at the slides right now. So the topic is reverse engineering iOS apps for fun and profit. And that's actually, the topic is twofold. In my past experience, I used to do both. So I used to just reverse engineer iOS applications for fun. And as a security researcher, I used to do it for profit. So for profit means what we did were black box tests, for example, where we analyzed applications of our clients and found out if they had any bugs or security issues. Before I start with the meeting, I want to make sure that you know what you will be expecting, and especially what you can't expect from my talk. So what I'm not talking about today is how to jailbreak your phone. It is necessary to have a jailbroken phone in order to be able to use some of the tools we use for reverse engineering. And I won't cover how you get your phone into a jailbroken state. So that's up to you. But I think there's a lot of documentation online. And the second part, if you think about reverse engineering iOS apps, one scenario that comes directly into mind is cracking App Store applications. And we won't do that today, actually. So if you have never heard of it before, all apps that are submitted to the iOS App Store are encrypted. And in order to reverse engineer an app, you actually have to decrypt them, and that is the process of cracking an application. And usually there is a malicious intent when cracking an application. So for example, some people will download applications, crack them, and then, for example, use, just provide them for free if it's a paid application. And that is absolutely discouraged by Apple. You shouldn't do that. And therefore, I won't be covering the part where you're cracking applications. So, but you have to keep in mind that if you really want to reverse engineer an iOS app, you have to decrypt it or have it in a decrypted state. But for our presentation, this shouldn't be an obstacle. because I will mainly talk about how to reverse engineer applications that you have either for beta testing, or if it's even your own application and you want just to try out, then it won't be encrypted. And we will see that in detail. So yeah, as I've started in the beginning, so the question is, why would you even want to do reverse engineering? And yeah, from my experience, what it looks like today is you usually use Xcode for development, and Xcode provides you a magic button, which is the so-called play button. And it does actually all the compiling and produces the application in the end. So you actually never have to think about how to forward engineer an application or how to reverse engineer an application. So I've brought one example today, which is an application that I've prepared for. Oops, that was too far. An application that I have prepared for today. It's called the OneTube app, and I will later on show what it does in detail, because we will be reverse engineering this application, and in order to make it more interesting, we won't look into the source code for now. So as I've mentioned, I have an iPhone attached to my Xcode, as you all know from your daily life as iOS developers. And if I want to run the application on my phone, I will just click the play button, and it will build the application, bundle it, transfer it to my phone, and run it. So that's the easy part. And if you want to know more details about how it works, you can always go to the log of the of Xcode, and here you can see what actually happens in the background. So the application was built at 6:16 today, and it was run at 6:16 German time. And if you go into the protocol, you can see all the steps that Xcode is doing in the background. And that's everything that is necessary in order to get the app into a runnable state. So that's what we call software engineering or forward engineering. And the idea of reverse engineering is you will get back from the built application to something that resembles the source code in order to analyze an application, or in order to change an application. So it's two parts: either analyzing and understanding how application works, and the second part is actually modifying an application, which can be part of reverse engineering. And we will be doing both of the parts today. So in order to step back to the initial question, so the question was, why would we even reverse engineer? One answer to that question is, if you learn how to reverse engineer an application, you will actually become a better developer, because you understand the tool chain that you're using better. You will know what the compiler does. You will know how the binary looks like. You will understand how, for example, libraries are linked and how the interconnection between components work. And it will make you a better developer. The second part is what you can do is actually debugging an application. And you can think about, for example, if you're using third-party library bundled in your main application and it produces bugs, then you could debug the third-party library, for example, and find the source of the bug, and maybe fix it yourself by patching, or adapt your code so it will continue working. That's the second part. Third part would be obviously reverse engineering in order to pen test an application, for example, a black box test, where you want to know if an application is attackable from attacker's perspective. And these are all valid reasons to reverse engineer your own apps or apps that you want to analyze. So we want to know what's happening within this process. The process is actually, you will code your source code, for example, in Swift, but it could be other languages too. So if you're talking iOS development, it's not always Swift. When I started developing iOS applications, there even was no Swift language. We started with Objective-C, and once we reverse engineer the application, you will see that even with a Swift application, a lot of the code that runs beneath is still in Objective-C or bridged to Objective-C. And this is the source of our applications. Then we have Xcode, which takes all the steps necessary to build an iPhone application bundle, an IPA, and this bundle will be transferred to your machine. So that's the usual build process. If we look at it from perspective of source code to machine code, we have the compiler sitting in between, and this could be the compiler for any language. So we could write C code, for example, even in an iOS project. Then we would use a C compiler, and the C compiler would actually create the machine code that is running on the machine. And the same is the case for Swift, and the Swift compiler would create the machine code that in the end is running. So we have two programs displayed here which do exactly the same. They will print out hello world on the console, and one is the C implementation, the other is the Swift implementation. We can see that the Swift implementation is a lot easier to understand than the C implementation, but both of them are a lot easier to understand than the machine code that sits below. And that's actually the reason why we are having higher level languages. It's because we can comfortably program in efficient and fast manner and don't have to worry about the underlying CPU, what it does, what it requires. You can just build one code basis and even compile for different CPUs. So that's the idea actually behind compiling an application. It's really an oversimplification at this point, and we will see a lot of those oversimplifications in the upcoming slides, but it's just to grasp the concept of compiling, which shouldn't be a mystery for you. So if you're looking at your applications, once you press the play button in Xcode, the compiler will run in the background, managed by Xcode, and will do all the necessary steps, all the linking and compiling that is necessary in order to get a running application. So in detail, it looks even more complicated, and even this is an oversimplification. In detail, it looks like this. We are actually not compiling for the target machine directly. So if we look at the last picture on the last slide, there is just one arrow pointing to the machine code, but this arrow hides actually a lot of intermediate steps. So this diagram shows what's actually happening in between. If you have an iOS application, you're actually compiling with a so-called compiler front end into LLVM intermediate representation. This is you can think about it also in terms of machine code or assembler code, but it's easier to understand than assembler code. So it's a higher level, but it's closer to the machine. And in the end, you will have an LLVM backend compiler, which will compile the actual machine code. So that's the reason why you can build Swift applications in Xcode and then compile for ARM platform or even for Intel platform. This would be possible. And we can do the same with the C code or Objective-C code. And whenever a new language pops up, so if Apple decided tomorrow that they will abandon Swift and create a new language, the first part that would happen is they would write a new compiler front end for that language that compiles for LLVM intermediate representation. In order to like see that hands-on, I will try to compile both Swift code and C++ code on the command line. So we can actually switch to the command line, and you'll see that I have a C program prepared. That's actually the example that I have in the presentation deck, and we can take a look into it. So this is old school programming. So that's what we did when I started programming. Is like you would have a text editor, input your code, and that's just basically a main routine, and then it prints hello compiler and returns 0. So if you have Xcode installed, you will have all the compiler components already pre-installed on your system. And that's why you can simply use the compiler that is bundled with Xcode. And because it's a C program, I will use the C compiler, which is called Clang. And I will do just Clang hello C. I have a warning because I have an extra character. We can even fix that, and that's what we used to do when we started programming in the past. It's like, covering all the compiler warnings and errors. So if I go back to the application, you can see that I have here an extra character, and I will just remove it, right back to the file and compile again. This time it works without compiler errors. And if I look at the list, I have an output file. And this is actually, if I try to see what kind of format the output file is, it will show me that it's a MachO 64-bit executable for 64-bit Intel processor. That's the case because I have compiled on my machine for my machine. So the application is directly executable, and if I run it, it will show hello compiler. So that's how you would compile C code by hand on the command line. And the second demo would be compiling the same, doing the same for Swift. So I have a hello compiler Swift file, and if I step into that file, you'll see that it's just one line of Swift code. And this time I will have to use the Swift compiler front end, which is called SwiftC. And then I will just input the Swift file, and it should compile without errors and warnings. And if I look to the file, we have an additional file, hello compiler. And if I check what kind of format that file is, it will show me again that it's an MachO 64-bit executable. And therefore, I can execute it on my machine, and it will output the console as we have intended. So that's actually the process of compiling the file by hand. And if I go into the man page of corresponding, well, there's no, sorry, can't forget about that. So if we go back, that's what I actually wanted to show you. If we go back to the build protocol of Xcode, and if you dig deep into it, you will find the SwiftC commands, and you could execute them file by hand. I'll spare you the details, but if you ever wonder what's happening in the background when you're building your own applications, you could just hit the build button, make sure that you clean the build folder, which you can do about in this menu, product clean build folder, so that all the intermediate files are deleted, and it will start the whole build process, and then you can build. And here you can actually watch Xcode executing all the steps. And here's the step where it says compiling Swift source files, and it will compile every Swift file that is present in the source folder, and that is necessary. So that's actually what happens in the background. It will call the SwiftC compiler as we did on the command line and compile every application. So stepping back to this part is what we actually saw right now is the SwiftC compiler, which is here in the middle, and how it's executed, the Clang compiler. Clang stands for C language compiler. And we could even have other compiler front ends for other languages. So this one we saw that. And the question is now, what actually is found within the the executable file. So I have one handy tool for you if you ever happen to analyze binary files. There is a tool called HexFiend, which is a raw hex editor that you can use. You could do that on the command line too, but I think it's more comfortable. So I will just start HexFiend. Updates right now. Okay, and I will step into the demo folder and drag and drop the hot file. And here you can see that's quite a lot of zeros and ones, and that's the MachO file format magic that you can see here in the first bits. So every file has like usually the magic identifier that tells you which file format it is, and this one shows you that it's a MachO file. So I'll make it just a little bigger so you can see it, and that's the compiled binary for our C code. And here you can see the ASCII representation, and we can even see that we can see some strings and some parameters. So there is something readable and other parts are not readable for a human being. If I open the other file, which is the compiled Swift file, then you can see that it has the same magic identifier because it's the same file format, but although the applications do quite similar tasks, it looks different actually because you have information about the binary. The question is, where's the code hidden in here? So just looking at it with a disassembler doesn't make it reappear for us. So we have kind of reverse engineered the application because we can look into the file, but we are not, we don't really know what the application does at the moment. So what is the MachO file actually? So how is it built? And if you're really interested in how it works in detail, you can check out the link that is in the top of the slide, which is a GitHub project which documents the MachO file format. And a simplified diagram is presented right here. So the first part is the file magic, the blue box. This is the first bytes that we looked at earlier. And then every MachO file has a header, which contains some information, and then it contains some load commands. After the load commands, there are some segments, so-called segments, and each segment can consist of one or two sections. So depending on what information you want to get out of the binary file, you have to analyze one of these areas, either the load commands or the segments or the sections. And they have different sizes, and if you understand the MachO file format fully, you can actually analyze what's within the executable file and find the code in there. For starters, let's go back to the. So you would see that the first bytes are the file magic, and as you can see here in these parts, you see, for example, here this could be some loader information because you are seeing libraries that should be linked, and anything that should be linked is actually an instruction for the loader on where to find libraries that should be linked against the application. But as we can see right now, it's more comfortable than looking directly at the zeros and ones, but it's actually still not comfortable enough. But luckily, there are some projects that try to build like MachO viewers, and I find this one very useful. You can find that in GitHub too. So it's an open source project, the XMacroViewer, and we'll actually try to use that in order to find out more about the application and reverse engineer it. So I just started here from my applications. So I have it pre-installed. It's the MachO viewer. If I go into my demos And let's just take the compiled Swift example and drag and drop it in here. We get a representation that looks way more handleable than just the hex representation. And I already get some additional information. So we can here see that this file was compiled on macOS on 64-bit machine. It was compiled with the Clang compiler, which we already know because we did that by hand. And it was the Swift compiler was used, and it was built on macOS SDK 12.3. And here we can see additional info like the file name, file size, etc., and the 5 hashes. Here we have the hex view. That's the same that we could see in HexFiend, and you can recognize the magic again. And the disassembler shows you actually the disassembled code. So we already found the code of the application, and as you can imagine, it's harder to read than Swift code. So the one line of Swift code that we programmed generated this much of assembly code. And here you can see the segments. So as I told you, you have segments, and you have the sections within the segments, and that's actually where you find all the information. And here you have the linking information. For example, we recognize the string that we found earlier, which are the linked libraries. And you can actually find out here more about the application. So there's the symbol table, which contains all the symbols that are used within the application. It's not that much for this application because it doesn't do that much, but we'll look later at an iOS application in order to find out more about the process. Here's actually stubs section contains function stubs that will later on be replaced with implementation of external libraries. So it's very complex, and you can spend quite some time trying to understand everything that's within the code segments. But as for now, we'll leave the application, the MachO again, because we have another important question to answer. So it was easy to analyze an application that we were using, that we were compiling by hand, and which just contained one source file and one executable. But the question is, how about iOS applications? How can we find the MachO file in iOS applications? Because in the end we have an IPA file, and that's actually not a MachO executable. So we'll have a look at it. So if you ever wondered how you can create an IPA file for analyze it with Xcode, it's actually usually once you have finished your application and want to publish it to the App Store, you would go and archive the application, and that's actually what creates an IPA file and uploads it. But you can even export the IPA file and use it for example, distributing it to team members of your development team. So that's what we'll be doing right now. I will archive the application, and here you can see it archived. And if I click distribute app and then select the bottom part which says development and go to next, then it will set to automatically manage signing. It will create an IPA package, and I can drop it in my target folder. So just to spare some time, I've already done that. So let me just go to that folder. So we have the OneTube IPA, and we can actually rename the file and just replace IPA with zip. send out a warning, and we'll just tell it to use zip. And once we have done that, we can extract the application. And it will output a payload or payload folder, and the payload folder will contain the actual app folder. And as we can see, there is not much to see. We could think that this is the executable, but I will just show you what it is actually, because it isn't. So I will go back to the command line, into my folder. If you look at it, there's the OneTube app folder. So I will dive back into that folder. And if I go into that, you can see the payload folder. So I will step into that. And then there's the OneTube.app folder, which is actually a folder. And because it has the .app extension, macOS will just not display what's inside of it. But it's actually a directory. So if I go and say cd OneTube app, and that's everything that's in there, you can see it. And even in the GUI, macOS graphical interface, if you right click and say show package content, then you will actually see what's within the applications. And here's actually the OneTube binary. You can see that because it says exec. And in the command line, if I try to find out what kind of file it is, file OneTube, it will say MachO 64-bit executable, and this time for ARM64, because it's an iPhone application that we built, so it's not for Intel architecture. So we are one step closer to reverse engineering our main iOS application. And actually what the file command does, it will check amongst others, it will check the magic bytes of the file, and then it can tell you that it's a macO 64-bit executable. So we're actually pretty close to reverse engineering. So we did an EPA file analysis, but that just works if we have an EPA bundle that we can analyze. So in the beginning, I talked a bit about App Store applications. Usually you don't have App Store applications ready for analysis. And because you install them via the App Store directly on your device, and there is no official interface where you can download third-party EPA applications. And that's the first point where actually a jailbroken phone comes in very handy, because you can extract the executable file from your phone actually. So I have my phone attached to via USB. You can see it on the right hand. I'll just start the application, start the phone. You can see that the OneTube app is already installed on my phone. So I will just connect to my phone via SSH. And I'm actually in my iPhone. And try to find the application within the file system. I will start at the root directory. And because I know quite a bit about the file system, I know that the applications are located in var containers bundle application. That's the path within the file system of the iPhone where you find all the applications. And if I look at the list of applications, they have random UUID installation paths. So I could step into every directory and see which one is my application. But I make it easier by displaying, sorting them by installation date. And I know that I just compiled that at 6.16, so this should be my application. Let me just step into that directory. Oh, it's a 0. For 4, that's the directory. And if I just can see that it's the OneTube app folder that we had on the extracted EPA also. So I will just go into that directory, OneTube app, and ls anything that's in there, and you can see that's the same structure as in the EPA, just located on my phone. And if I try to find out what kind of format the OneTube file is, you can see it's MachO 64-bit ARM 64 executable. So that's actually the binary. So I could now copy that binary back to my device, and then would be able to analyze it in the same way that I extracted it from the EPA. So it would be identical. So that's that part. And right now we know where to find the MachO file. We know how to extract it either from EPA or from phone. And we know that we can use XMacroViewer to see what's in there, and somehow it will help us to find the disassembled code. Question is, what can we do with that knowledge? Is in order to actually analyze an application, it is handy to know the assembler language. This is just an example of a let's say a very simple CPU architecture that just contains a few assembler instructions, and you can think about it in terms of you have several basic blocks, and everything that is computable can be built out of these basic blocks. And the basic blocks are usually add commands, logical commands like instructions like AND or XOR, multiplication, anything like that. And they are usually numbered. So the CPU knows that the instruction with the code 000 is actually the add instruction. The instruction with the code 001 is the AND instruction. So they are just numbered like that. So if you think of a very simple CPU, and you would have like a computation like 5 plus 6, just to make it a very simple example, the corresponding assembler code is add 5, 6. So it's constructed of a instruction and then left-hand and a right-hand operator. And these are called immediates in assembler code. And the assembler code is actually not the real machine code. So assembler code is actually already a high-level language that is used in order to make it more readable for human being. If we step back to our previous list, the add command would be the 000. So in bits, it would be 00056. And if you transfer 5 and 6 to binary, it would be 000101110. And that's the machine code that is executable. So if the CPU comes across that instruction, it will analyze the first 3 bits, see that it is an add instruction. Now it knows that an add instruction has 2 operands, and it will interpret the next bits as the left-hand and right-hand operand, and then execute the command. That's how a very simplified version of a CPU would work. In reality, the machine code instructions are 64 bits long on a 64-bit ARM architecture, but the structure is essentially the same. So in order to understand what an application does, we would have to know all the assembler code. And if you look at it, you can find it online. It's the ARM reference manual, which details all the commands that can be run on an ARM CPU, which is implemented with iPhones, and it's like 800 to 1,000 pages. So it's very, very tough to understand and learn, but it's possible. So you can get to a degree where you're comfortable reading disassembled code. And that's actually the first step in reverse engineering, is running the machine code through a disassembler. And we have one actually bundled within our Xcode toolchain. I will just step back into the demo directory. Demo. I'll just use the Swift example again. And you can use OTool, which is an object tool bundled with Xcode, and we can use these flags in order to get the disassembly of a compiled application. So if I do that, as you can see, So I don't expect you to understand any of these commands, but you can see that it's the structure that I explained earlier. So here you can actually see an add instruction on assembly level, and it has two operands, as I explained. So this is the left-hand and the right-hand operand. I know that you can't make much sense of it right now, but that's actually what you would need to be able to read in order to understand assembler code and make sense out of these bits that are actually there. So that's the whole disassembly for the simple example of the Swift code that just prints one line of code. And if you remember in the XMacroViewer, if we stepped on the disassembler part, we could also see these instructions. And here you have quite a lot of AND instructions, compare instructions, move instructions, so memory handling. And actually doesn't mind how complex your application is. In the end, it will boil down to simple assembler instructions. As a very good reverse engineer, we would be able to read, understand these assembler language instructions, and then even manipulate them. So patch them directly within the code. So if I know what the identifier, for example, of an add instruction is, I could just step into that part of the file with a hex fiend and then just change a 0 to 1, and then it would be, I don't know, a multiplication instead of an addition of two parameters, and then the program behavior is changed. And there are even examples where you can actually patch a complete routine to do the opposite of what it's intended to do by just patching one bit. For example, just think about an application that has an if statement, and if A is true, then it will do X, and if A is false, it will do Y. So in the end, this if statement is just built with one branch instruction. In assembler, it would say branch to that part of the code if this value is equal to that, and otherwise branch to the other. And if you just patch that to do the opposite, to branch or not equal, which is just one bit, it will be the opposite behavior of the application. Stepping back to our main routine, is the question is, it's not very comfortable even with XMacroView, which is way more comfortable than doing it directly with hexfiend. It's not so comfortable to use disassembler on the command line, and that's why there are actually commercially available disassemblers. The most prominent one is Hexrace Ghidra, which is the interactive disassembler built by Hexrace. You can check that out on their website. And that's like the industry standard for reverse engineering. For iOS, we have a special candidate, which is Hopper app, which I like to use because it's actually cheaper and specifically built for iOS. So if you have iOS, if you want to reverse engineer iOS application, it's the go-to disassembler. And then there's Ghidra. Ghidra is very special because it's open source and freely available. The interesting part about it is it's actually built by the NSA, and they are providing it for free to everyone. So if you're comfortable running code that was built by the NSA, you can use Ghidra for free for reverse engineering. I would recommend using an air-gapped machine, or at least a virtual machine, in order to not have any side effects for your personal data or anything. So what we will do right now is actually we will use the demo version of Hopper. So if you want to tinker around with it, there is a demo version of Hopper available on their website, and you can just download it and try the demo. And the restriction of the demo version is that you can actually just run it, I think, for 30 minutes, and then it will auto quit. So it's good enough to play with it. And what we will do is actually, now that we have the binary identified in our iOS application, we will just use the binary. I have it here in the one tube. app, and I will just copy that over, copy it here, and drag and drop that into Hopper to automatically detect that it's a MachO binary for 64-bit ARM, and will try to auto-analyze the application. You can see that it does some analysis steps here in the log, and in the end it will say once it's finished, it says background analysis ended, and then you can start actually reverse engineering the part of the application that you're interested in, and it's it will usually take some times for real applications, but because we're having just a small application, it took just 200 seconds, or not even that, I think it was milliseconds. And what you can see is here you have the main content, which shows the disassembly, so that actually looks very similar to what we saw earlier, but we have here labels, and here you can already see some part of it that will look familiar for you. You have here like a view controller code, and you can see that I have the one-tube view controller, and here I can see the view did load method, and here I can see the particular implementation of that method. And the interesting part now with reverse engineering is that usually disassemblers will also come in with a handy decompiler. So I can step in any part of the disassembly, just hit the decompile button, and it will show me a more readable version of the disassembled code. So if I look into that, it will just show me that it calls this, the view.load function calls a different subroutine, and then I can double click and step into that. And here actually I can see quite a lot of familiar code. For example, here it says view.load, here it says UI pasteboard, and here general pasteboard. So in order to disassemble the application or reverse engineer right now, I will first show you what the application actually does. And then we will try to find out how we can see that. So I'll step back to my phone, and as you can see, there is the OneTube app right on the home screen. And what the application itself actually does is you can copy any YouTube video link into the pasteboard. Here I have the video of the WWDC from last year, and if you start the application, it will just grab the URL and play just that video. So that's why it's called OneTube. It just plays one video in an infinite loop, and it will grab the video content from the pasteboard actually. So you have to copy the code first. So try again. We'll just copy that URL, copy, start the application. It will detect that it was copied and pasted, and you can start it and it will just play. So that's the application. So one idea that we could have is actually we want to manipulate the application and find out as an attacker which video it is playing. So if we step back into our disassembler, we could it makes now a lot more sense that we are seeing references to the pasteboard. So in iOS, if you want to access the content of what is in the pasteboard, you have the UI pasteboard class, and there is the general pasteboard method, which will return the general pasteboard of the operating system. And if you call the string method on it, which you can see here, then you will get the string representation of what is actually within the application. And if we were an attacker, for example, and want to know which video the app is actually playing right now, we'd have somehow to find out what is happening in here. But yeah, from that point, actually now from the behavior combined with what we're seeing in the decompiled version, we can already derive the behavior. We can understand what the application does internally, and that's actually the first part of reverse engineering. So if I step back to our timeline, so we did a demo disassembling with Hopper, and now the second part would actually be manipulating application, and therefore we would try to hook the application. And what comes in very handy is actually a hooking framework for iOS, which is called Frida. And I'll just show you the website. So frida.re is a very, very common dynamic instrumentation toolkit. So you can use it in order to hook any application that is running on your iPhone. It is, you can just install it with pip. So if you're familiar with the Python programming, there is it's a Python tool, and you can just run it into a virtual environment and then start analyzing the running application. So it's dynamic analysis of what is happening on your iPhone. And we'll just step into that directly in a hands-on manner. And I'll step back to my command line. I have to SSH back into my phone because we are, no, actually I don't have to do that, sorry. So I have Frida pre-installed, and you can see that if I type Frida and do the tab completion, you can see all the different Frida tools. The first one that I'll be using is Frida PS, and I will give it a -u handler. So what this actually does is list all processes that are running on the iPhone that is attached. So we start OneTube and then do Frida PS, and it will have quite a list of applications running, and we will want to find out which one is our application, but we already know the name of the application, so we could do something like grab OneTube, and Frida shows us that OneTube is running with process ID 2205, so we actually know that our Frida installation is working as intended and delivers the information that we want, runtime information about the iPhone. And now we would want to find out what the YouTube application is actually copying from the pasteboard. So for this one, we'll use the freetrace function, which is actually a function that you can use in order to find out all the function calls that an iOS application is running. So the whole command would look like this. It's like freetrace, then -u for USB, and then -m for tracing a specific function. And we are interested in the UI pasteboard string function. And that's what we derived actually from the disassembly of the application. So if we step back to the disassembly, what we found out here is that it uses the UI pasteboard, general pasteboard, and the string method of that class. So what we're actually saying here is trace that function and outputs information if the function is executed within the application. The -f specifies the app ID of that application. So even if it wouldn't be running, so I will just, for now, close the application and then hit enter. And you'll see that the application started, is running, and you can see that the trace worked. You can see that it created a log file and said after 131 milliseconds, there was one call of the application UI concrete pasteboard string method. And the second part is that Frida auto-generated a JavaScript handler at that location on my disk locally that can be used in order to hook the application. And what we actually want to do is just log the parameter of the URL. So I will just disconnect again from the application, just stop it, and then I will manipulate that JavaScript file. And here you can see this is auto-generated by Frida, and it contains actually the boilerplate code that we can use for hooking methods on Frida. So this one was this method has this file has actually two functions implemented. One is on enter, has 3 parameters: log, args, and state, and the other part is on leave. So it will be executed once the traced function is called, and what it actually did right now is it just logs the name of the function, and that is what we saw in the command line. What I actually want is to log the return value of the application. So this is of the method, and this can be done in the onLeave function. So I will just step into that, and you don't have to really understand the details on what you're doing here. There is plenty of documentation on the Frida page, but what I will do is I will just, as you can see, the onLeave function has 3 parameters, and the one I'm interested in is the return value. So I want to log the return value. So I'll just create a new variable, which I'll call current URL, and then I will say new objective C object well. And then I will log the current URL. So two additions to the boilerplate code. Once I create a new Objective-C method out of the return value, and then assign it to JavaScript variable, and then I will log the variable. So that's it. I will save and exit. And now if I run the hooking command again, it will just use the JavaScript file with the modified content, and will do whatever it states in the onLeave and on enter functions. So if I hit enter again, it will start OneTube on my phone again. And as you can see, additionally to logging the method name once it was executed, it actually outputs the URL that was actually copied from the pasteboard in the onLeave function. So the modification worked. So now we have traced more details about the application, and now the final part would be patching that application. So I will again step into that JavaScript file and just add one additional line, and let me just prepare it. I will step back into the onLeave function and add one additional instruction, and this is the replace method of which Frida gives me. So it lets me replace the return value of that method, and I'll just create a new string and give it a different YouTube URL. So it should, if this code works, then it shouldn't be playing the YouTube URL that's present in the pasteboard, but it should be playing the YouTube URL that I've given the application. And we can just test that out by hooking back into OneTube. So let me just stop the application again, and now start and hook it again. And I think it worked. So we have replaced the URL, and it's playing a different YouTube video. And that's actually how you manipulate iOS applications in real time. I will step back to our timeline, and that's actually the conclusion of my course, so of my talk today. We could step down now in detail and try to figure out how to hook different methods, for example, network methods, or like data storage, or anything that you can imagine. But I think that this would be really an interesting talk for a third session. So I'm open for your questions right now, if you have any. And thank you for your attention.
Very nice. Shoot.
So
Right. Any questions, guys?
Yes.
Well,
So, maybe
we will
just,
get some questions. We
yeah.
can. Yeah.
Yeah, definitely.
SwiftSofia says thank you. He doesn't want to ask any questions, but
Okay.
I think it was pretty good, Rashid, and I think this it was a nice, very nice presentation. But I think it's worth this is worth a workshop. You know.
Yeah,
not just-
yeah. I think it's really the tip of the iceberg. So now you can step into the interesting part, and it really depends on the kind of application you want to disassemble, analyze, and what purpose for. So you can. It's a very mighty tool set.
Yeah, well, a lot of tools. So yeah, definitely. Definitely, the third one should be like a workshop
Yeah,
that you
yeah. I
make.
think so too.
That would be very nice, and I think people will enjoy. At least I will enjoy it, definitely.
And if you come up with any questions, so you will get the slides anyway, and there will be all the tools linked. And yeah, you can rewatch the video if you want to actually do it yourself by hand. And I'm pretty sure you will come up with questions once you try out the tools and something is not working as expected. But you can contact me and I'll try to help.
Well, that's good to know because I'm sure people will need help with this.
Yeah.
Have you? Okay, maybe I can ask some questions. Like, have you? I mean, you showed us a jailbroken phone and an app there, but can you actually do this with a real phone? I'm sure you can, but like, can you do it?
Yeah, you can do it actually. Actually, it's not even just possible, but also necessary. If you think about, you want to really pen test an application, you wouldn't really want to run all the tests on a jailbroken device because it would actually produce false results because the execution environment is different than from a real phone. So what you can do is Frida is available as a dynamic library, and you can link that library within your application, and then you can do it on a regular jailed phone and just use it from a command line like we did as if it was running on a jailbroken phone. You can trace anything, or let's say, for example, you have a application which you should test or you need to test, which is distributed via test flight. So your beta tester, for example, for an application, then it wouldn't be decrypted because it's not a real App Store application. You could just download the EPUB file, then link Frida into the application, run it, install it, run it, and then you could do the same on the jailed phone.
That's pretty cool. Yeah. Okay. Well, I guess I'll have SwiftSwap's question.
That's really good question. I think most of them are heavily maintained, so they should, but I'm not sure as I don't have an M1 Mac. Oh, I have one, but my wife has one, so I could test on that.
But that's the same architecture as the phone, so it should be that should be interesting.
Yeah, but if you think about some GitHub projects which are not recompiled or anything like that, then it would be definitely. So yeah, most of the tools are open source, so should be able to compile for M1.
Well, that will be.
Or Hopper, I'm not sure if it. So.
Well, I'm sure you'll check. So.
Yeah.
Well, you started talking about that you can test a real app through TestFlight, etc. In your work life, have you done it, or like how often do you do it?
Yeah, it happens. Yeah, actually, quite frequently. So as you can imagine, we have suppliers, which will supply us with software that we are using as a company. So B2B suppliers, and usually they will first deliver features via beta function, and then we will be testing those applications and then telling them if we can run them in the wild. So that happens actually quite a lot of times.
I guess then it's good it happens often.
Yeah, and actually it would be easier to have the source code and just look into the code. So actually white box testing is way simpler than black box testing if you can look into the code. But as you can imagine, most developers look at their code as their intellectual properties. So unless you sign an NDA, then you won't be able to get the real source code of the application. And black box testing with Frida hooking stuff makes it easy to just test a feature, find something out about it without accessing the source code.
Yeah, that's interesting. It's just that we don't. I mean, as iOS developers, day to day, I don't think we think. I don't think about this that much. I hope
I think the most interesting part in a developer life for reverse engineering is actually third-party libraries. How often have you come up with a library that just doesn't work as you think it should, or has a bug or something like that, but you're bound to use it? And if it's closed source, then you can't even look into it and see what it does. But reverse engineering it, decompiling, you can understand a little bit about how it works internally.
So that probably means you often look into Google libraries and see how they work.
Yeah. Or maybe you can patch you could even patch behavior of the library. So if it does something that you don't like, just patch it out.
Well, I know you can do that with Swizzling in a way, as a more standard way, right?
Yeah.
But say if you, say I want to patch a library, not like Swizzle it, but like do it with instrument. That's also possible.
Yeah.
Well, that's pretty cool. Okay. One more reason to start reverse engineering.
And it's fun. Actually, it's my preferred part of app analysis. So I find code reviews very boring. Where you have to scroll through pages of code, but reverse engineering is always has like some. It's pretty interesting. Get a first idea on how something works, and then you manage to patch it, and it's a success, and you feel good.
That sounds better, because the style of things I do at work, sometimes I do really get bored with them. So that's like another way of looking.
That's a really good question.
Let's see.
What's the most shocking thing you've uncovered via reverse engineering apps? The most shocking thing, actually, if you do code reviews, then, and that's also part of analyzing applications. The most shocking thing is that most applications contain major flaws. So it's not about is there something that I can find. It's just about like how many flaws you'll find within an application. It's just so much. I think that's the most shocking part.
Well, but yeah, that sounds shocking. But okay, I can add to that question. There's a lot of flaws, but are a lot of these flaws coming from like the ecosystem itself, or Yeah, okay.
True.
That was a quick answer.
Okay. And if you think about local authentication, I always look at application from a security perspective. So local authentication, you'll input a password and then it lets you in. So, or it declines if you have the wrong password. And that is a function that you can really patch with one bit within so many applications, if they do it on the client side. So like there's no server authenticating you, just the client, and will check the password. And it's just if wrong, then proceed to the next screen. And if you switch that around with just one bit flip, then it does the opposite, and you will get in with any password except the we won.
Okay.
Because it's flipped.
Well, it's okay. That security with passwords is like a whole other story. I don't. Well, maybe I can add more. And yeah, I think it was like a month ago. Okta shared that they got hacked and etc. I mean, are you aware of that? And like, do you have like some inside information about that?
I don't have inside information, so everything I know about it is from media, like everyone else, and they are obviously not very communicative about what happened inside. But it's
Yeah,
a big issue.
because we use it at work, and I was wondering if something's gonna happen, and we haven't heard anything about that since that news, but just wondering.
Well, for example, let's say if you remember the Log4j vulnerability,
Oh yeah, well,
beginning of the that would be actually a pretty good example for reverse engineering and patching, because if you found out that your system contains Log4j and it is third-party software, for example, and the software developer doesn't provide a patch, and you could just reverse engineer that part, patch it, and then it's fixed.
Okay, that makes sense.
So for security reasons, it's if you're like doing security protection for someone, then it's really important to have that in your skill set.
Well, hope whoever is doing that does have that skill set.
Yeah. And we hope that the errors don't get done in the first place. So
yeah, well, that of course, but we can see that this happens. I mean, sooner or later, it's going to happen.
Yeah, no way out.
Yeah. All right.
Okay.
Well, I think I can't think of any more questions, at least for now. Guys, do you have any other questions?
Okay.
Seems quiet. I guess it's well, we'll have a recording for the video, and I'm sure people will be able to add their questions under the video, under the recording. So we'll share that with you too, Rachid, and you can answer there if you want, or they can write to you. Your email is in the event. So
yeah, wonderful.
Thank you again.
Thank you very much.
It was.
Oh, that's a huge compliment. Thank you.
Yeah.
And next time we'll try to be better than WWDC.
Well, if you can do that, I'm sure there will be a lot more questions. And I hope you are. So.
Yeah, I'm open. We can do more parts.
Oh, definitely. Next time at least if you ask me, I think we need to do a workshop live and like get hands-on.
Yes. And if there are like any parts that you're interested in, then you can send out the topic, and I'll try to see if I can do that.
I'm certain you're going to be able to, but yeah, we need to find the time. We'll find the time.
Yes.
All right. Well, thanks again, Rachid. I guess we'll stop broadcasting now. And yeah, thanks again. It was very interesting. I'm sure everybody who attended enjoyed it. And as I said, we'll have a recording so people can watch it afterwards and learn something. And yeah, what I wanted to say also for the people that are not in the SwiftSofia group, that's on Facebook, can join. And Rachid, you can join too.
Thank you very much.
If it's not you doing online, well, let's hope we don't have to do online meetings anymore. But we do try to record the live ones too.
Okay, wonderful. So thanks, guys. It was pretty good.
Thank you. Yeah, same.